This lecture looks at one of the most useful techniques in Bayesian machine learning and data science more generally, known as expectation maximization. So to motivate the use of expectation maximization, we'll pick up from the topic of the last lecture, which concerned mixture models. And recall that a mixture model is a way for us to describe a probability distribution, or in this case a density function, as the sum of other density functions where they're indexed by particular groups, particular densities that they're from. So in other words, it could be a mixture of Gaussians, a mixture of Bernoullis, a mixture of binomials, whatever distribution we might want to have. And in fact, it doesn't even have to be a distribution. It can be models more generally. The question is, how do we estimate these parameters? And we pointed out last time that unfortunately the likelihood for this doesn't make it easy to maximize. So we'd like to estimate these parameters. And the answer to this question is we use this expectation maximization, or EM algorithm. The combination of the EM algorithm with Gaussian mixtures, where these mixing density functions, or Gaussians, is often used for clustering and more generally for unsupervised learning. The Gaussian version of this is called Gaussian mixture models. It's also called model-based clustering. So you'll hear both terms used to describe this notion of combining Gaussians in order to separate data and do unsupervised learning. We can also use mixture models with any distribution, as I pointed out. It doesn't have to be Gaussians. So in fact, if you use it for things like binomials or Bernoullis, it can be used for text analysis. And it's also used for more problems than just clustering. As I pointed out, you can mix it with, for instance, models. You could mix it with dynamic models. I've seen it used for prediction of tracks of hurricanes. So it's a very useful technique that has a lot of applicability. Well, we're going to focus here on these Gaussian mixtures. So let's start with the notion of what a mixture model is in this larger sense. The last class we looked at univariate cases. We're going to generalize that to a multivariate case. So again, we've got n independent samples from k distributions. These are our clusters, if you will. And theta, bold theta, is the vector of parameters for our particular distributions. And these are multivariate distributions. So if the probability that the data come from a distribution, and we'll designate that as phi, that's one of our kernel densities that we're going to use for this. And in the case of the problems we'll consider here, they'll be Gaussians. If that probability is pi, then the pi's represent, the pi sub i's represent the mixing weights that we have on each one of these densities that then give us our estimate for the overall density of our data. For Gaussian mixture models, we assume, as I said, these phi's are Gaussians, and we're going to give them a mean vector of mu and a variance-covariance matrix of sigma. We also create a random vector z, which is a latent random vector. In other words, we don't observe it, and it has as many elements as we have components in our mixing formula. So it has k components, and each of these k components is binary. So we use this z variable as a way to define our mixing probabilities. So in particular, if we look at any one of the components of z, the probability that that component is 1 is just the probability of being in that component, or pi I. Okay, so let's look at the parameters now that we have to fit in order to solve this mixture model problem. And obviously we have the probabilities, the mixing probabilities, pi 2 through pi k. And we've arbitrarily removed pi 1 because they have to sum to 1. So any one of these can be removed because it's defined as 1 minus the sum of the other ones. And then, of course, we have the mean vectors for each of the Gaussians, and we have the variance-covariance matrix for each of the Gaussians, 1 through k. The log likelihood, then, in a similar fashion to what we saw when we looked at the log likelihood for the simple univariate case with 2 components, Now we have the log of a sum of k components instead of 2. And of course, they're weighted by this mixing probability pi of k. So each one of the components then is the probability density, in this case the multivariate Gaussian, for observing a particular x value, one of the observations that we have in our data set, given the values of the component that we're considering. And we do that by summing over k of those components. Now it's that sum, the log of the sum, that makes it something that we can't maximize very easily, which is why we need this expectation maximization algorithm. All right, so let's set up some additional notation that we'll need for our use of the expectation maximization algorithm. And the first thing that we will use is this notion of a responsibility, which we'll designate gamma I. And this is a responsibility associated with a particular observation, I, from 1 through n, one of the observations that we have for a particular component, k, one of the clusters, if you will, in our mixture model. And this is nothing more than the probability that this observation I is a member of cluster k. And that's what we're interested in when we talk about the responsibility. It's the probability that that observation is a member of a particular cluster k. So if we look at the definition of this, then it's nothing more than the weighted product. It's the weighting or mixture probability, pi of k, times the multivariate Gaussian likelihood or density of observing that xi given the parameters for that component, which are mu of k and sigma of k. And then this is normalized by summing over all of those. So for all possible components, what's the probability that it's associated with it, or the likelihood that it's associated with it? We're summing over all of those in the denominator, and that makes sure that these responsibilities in turn sum to 1. Okay, let's look at the additional parameters that we have. Another one is nk. And once we have these responsibilities defined, then nk is really a rough version of the number of observations that we have assigned in each one of the components. Since the responsibilities, the gamma sub I, z of k, are between 0 and 1, then this sum is not an integer, but it is a soft measure of the number of observations assigned to each one of the components. Now when we look at the estimate for the mean vector for a component, one of the Gaussians that make up our mixture, then we can find that very easily, again, by using these responsibilities, the probability that an observation is a member of a particular component or cluster, times the value for that observation, x of I, and then we sum all of those and just take the average. By dividing by, what we just found is the number of observations in each one of the components. We do the same thing really for estimating the variance-covariance matrix of each of the component mixing probability distributions by just looking at the weighted average of each one of the sum of squares matrices found as the outer product of each observation's values subtracted or minus the mean vector for that particular component. And so that outer product then is going to give us the sum of squares. We're going to weight it by the responsibilities, and that'll give us a way to find the average when we divide by the number of components, the number of observations per component. And finally, we can simply find the mixing probabilities, pi of k, by the number of observations in each component divided by the total number of observations. Okay, so with this setup now, we can easily see how the EM algorithm, expectation maximization algorithm, will work for this multivariate Gaussian. So we first initialize theta, and we'll say more about what we do for initialization, but for the moment, just think of us as grabbing randomly some values for this and throwing them in those parameters that we need. The E-step then is really pretty straightforward. The E-step really involves just estimating the responsibilities. And we find that because we've created initial values for each one of those parameters, the pi's, the mu's, the sigmas. We just put those values in and we estimate the responsibilities with those initial values for those parameters. The M step then goes back and it says, okay, you did that. Now you're going to find the new values for those parameters. And the way we do it is, since we now have the values of the responsibilities, we can find, for instance, the number of observations per component just by using the sum of the responsibilities over all the observations for each of the components. And then we're going to do that as well for the mean vectors for each one of the components. Again, exactly as the definition of those parameters, we're going to find it as the weighting of the observations where the weighting is the responsibility assigned to that observation for that particular component. And then again, averaged by dividing by the number of observations in a component. Same thing for the variance covariance matrix estimate. This time, instead of the mean vector, we now have this sum of squares vector, which is the outer product of the observation minus its mean vector. And again, divided by our estimated number of observations per component. And finally, again, the mixing probabilities, the number of observations per component over the total number. We stop, we continue back and forth, going back between the M step and the E step, going back and forth until we get some kind of convergence. And the way we measure that is by looking for changes in parameter values, or more often we look as to whether or not the likelihood is flattened out, and then we stop. And we typically assign a threshold for that change, some epsilon that we say it has to be less than that threshold in order to stop. Okay, some comments on this approach, expectation maximization for Gaussian mixture models. Poor starting points can lead to really bad solutions, and we'll see that in a little example we'll look at soon. Some approaches to starting: you can randomly select starting points by randomly selecting from the data and using it to parameterize the initial settings. You can use some kind of clustering algorithm like k-means to first group everybody into groups and treat that as a starting point for the algorithm. You can do stratified sampling, and this is sort of a combination of the first two. You can first cluster and then stratify based upon your initial clustering, or you can do the stratification based on prior knowledge. Selection of K is typically done by just trying several values and seeing what the results are, and based on that, making a selection of the best K for your particular problem. You have to remember that EM is, at the end of the day, a heuristic, and it can get stuck in local optima. So it's not guaranteed to produce the best answer to this problem of finding these parameter values for this mixture model in this particular case. So it's best if you can try it a couple different times with a couple different starting points. Okay, so let's look at an example of how the EM algorithm works with these Gaussian mixture models. And this example comes from Theodoridis, and we have three Gaussians that are going to generate the data with the mean vectors as shown. And we have, in the case of the variance covariance matrix, constants, the sigma squared shown multiplied by the identity matrix. And we'll initialize in the first example here with these mean vectors as shown, and with the constants for the variance covariance matrix all set to 1. And the mixing probability is all set to 1/3. So we're equally likely to be in any one of the three clusters. So here are the plots that show how the EM algorithm works for this particular problem. The one in the upper left is the starting point. So the circles in black show a contour for each of the three generating Gaussian distributions, and the points behind them show the points generated by those particular Gaussians. And those points then constitute the data. Obviously, the actual Gaussians themselves and their parameters are latent variables. We don't know them, but what we do know are the values of those points in 2 space as shown. The red circles show the contours of the starting positions for the EM algorithm. So these are where we start our EM algorithm out. And in B, we show what happens after 5 iterations of the algorithm. And you can see that already one of the components, the one in the lower left, is starting to converge. The ones on the upper right are not there yet. But in the lower left, you can see that after 30 iterations, the algorithm has converged pretty closely to the underlying generating distributions. And in the bottom right, you see what the log likelihood looks like, and you can see that at about 30 iterations, or even maybe 25, it's starting to flatten out to show that it's converged to its answer. Okay, another way to view this, though, is with different initialization points. So these are sort of extreme points for the mean vectors. The other components have stayed the same. And when we look at the plot here, we can see again our generating distributions. Again, looking at the plot in the upper left corner of this slide, we can see the generating distributions in black with the data that they generate. And you can see that the starting position here is pretty ridiculous. It's in the upper right. Probably not something that we would use to start this algorithm, but at least it illustrates what happens when you have a bad starting point. And after 5 iterations in the plot in the upper right, labeled B, you can see that one of the distributions has converged pretty much, the one to the right, but the other two have not. And in fact, after 30 iterations, they still have not converged to the generating distributions. But when you look at the lower right plot, you can see that the log likelihood seems to have converged. So this is an example of where the algorithm would converge to a suboptimal point, or a local optima, I should say, that is not globally optimum for this problem. And that's the kind of problem you can get into with a bad starting point. So this lecture has given you an understanding of how we can use the EM algorithm, the expectation maximization algorithm, for mixture models. And as I say, it has much broader applicability, but once you see its use in mixture models, you can extend it. And in the next lecture, we'll look at how we can use the EM algorithm for another major topic in Bayesian machine learning known as variational inference.